Okay, my name is Noah Thibodeaux, as Dr. Magoo pointed out. So we're going to be looking at the impact of RCA parent strength on fresh and mechanical properties of recycled aggregate concrete. So just a little presentation outline. So first, the RCA background. So concrete represents a very large energy demand and obviously creates a very large volume of waste. If you think about how much concrete is produced per year, and eventually most of those structures will reach the end of their service life at some point or will need repair. So that's a lot of concrete that's being demolished and landfilled. So despite the availability of sustainable waste management techniques, CDW, or construction and demolition waste, is landfilled in very alarming amounts. So this is not only reducing our natural aggregate sources, but it's also increasing or it's decreasing our landfill space as well. So recycled concrete aggregate, as all of us probably know, is a processed form of concrete waste. And one of the key issues that we have is that there's a lack of consistent qualification and design standards. So it presents an issue when we're trying to design new structures or structural concrete specifically with RCA. We could definitely see a way that we could maybe produce sidewalks or curbs with RCA. In the very near future, it's even being done now in some places. But as far as using RCA for structural foundation, things like that, there's a lot of qualification and design standards that we need to meet before we can actually do that. So this is just kind of showing a typical cradle to grave life cycle analysis of aggregate. So first of all, we have the aggregate quarrying source, and that represents a very large volume of natural resource depletion. And then we move along to construction, and then demolition when the structure reaches the end of its service life. And then finally, that material that was originally, in its original form was an aggregate quarry, is now being landfilled. So what we propose is kind of breaking this cycle. And instead, we start with this processing of old concrete, and then into construction, and then demolition when that structure reaches the end of its service life or when there's a repair needed. And then segregation of the mass concrete pieces into smaller pieces, separation of rebar, and also cleaning of any deleterious materials, and then processing back into aggregate for new concrete. So in the current study, we have 3 parent concretes that we developed in the lab, and they were processed into recycled concrete aggregate for use in recycled aggregate concrete at different natural coarse aggregate replacement levels. So this is just kind of a very easy graphic just to kind of represent what we're doing. So we're taking these 3 different parent concrete groups, and we are replacing them at 20, 50, and 100 for each one. So you end up with 9 recycled aggregate concrete mixtures. So what we wanted to do in this study is to look at the early and long-term strength. So specifically looking at 7, 14, and 28 days, and then looking up to 90 days to see what the effect of RCA replacement was on F prime C, or the compressive strength, to actually capture the effects of RCA on recycled aggregate concrete. So 3 parent concretes were produced. These were actually produced by a previous student, and these strength classes were 4,000 to 6,000 psi. And these were poured as slabs and then broken up with a concrete breaker, and then they were further crushed down and processed. So in this study, what we're doing is we're using natural aggregate concrete at a known design strength, and we're testing it, and then it's being used as RCA, so that we know a lot of the properties about the RCA, so we can actually qualify different parameters. We can look at how the strength is affected, and even look at how the workability properties change as well. So the crushing process was set up so that we would get a number 57 aggregate, which fell generally within the acceptable limits when some of the fines were screened out. We didn't do a full processing, as you might see in the field or in some other studies. we were really trying to capture the effect of the parent strength. So we didn't want to employ too many processing techniques. So then these are just some of the standards that you would run a typical natural aggregate through. So we looked at ASTM C33, ASTM C127, and ASTM C29. And all of these parameters are needed to actually design a concrete mixture in accordance with the ACI concrete mixture design procedure. So we used the ACI mixture design procedure for all mixes, including the parent concrete. So these were done so that we could have the absorption capacity, which is needed to design the concrete mix, as well as the dry rotted the dry rotted density. And then we also found the gradation profiles of the RCA. And then another important factor is the adhered mortar content. So we looked at some studies, and there was a proposed method. There's 3 different methods. There's an acid solution method, there is a thermal method, and then there's another method that involves basically acid etching. So this process involves soaking the aggregate for 2 hours, and then heating the sample to 500 degrees Celsius for 2 hours, and then immediately introducing the sample into very cold water. What this achieves is it shocks the mortar matrix, and it causes it to disintegrate and to fall away from the natural aggregate phase. What happens during this process is that some natural aggregates may be split, but they do not disintegrate. So what this enables us to do is to look at the percentage of that system that is attached mortar. So this is just just to give you an idea of what this looks like. So this is the sample going into a muffle furnace, heated up to 500 degrees. So when this comes out, it's very, very hot. The pan is completely red. And then when you introduce it into water, there's a lot of activity that happens. And then you're able to take the aggregate out, drain all the water while keeping all of the solids, and then you basically break the mortar off of the natural aggregate, and you wait for it to dry to a SSD condition before you actually weigh the individual components. So this is just showing the properties of RCA and the properties of the natural aggregates used in the study. So what I really want to point out in this slide is take a look at the absorption capacity. So the absorption capacity of a natural aggregate is going to be about 1/10 of what we would see in RCA. So when you're actually mixing RCA, it's very important to be careful about how you condition it, and definitely add enough water to that system, because if you don't, then you'll have the old mortar phase is going to, once you suck up a lot of the water that you're adding to the system, and you can end up with a really bad mixture. So it's very important. It's more important for RCA to get your aggregates to an SSD condition so that you can actually use it in mixing. And if you look at most studies involving RCA, this is definitely an important factor. So again, as you can see, our size gradation is the same across the board. So for our parent concretes, we achieved a number 57. And for our natural coarse aggregate, we also have a number 57 aggregate in the lab. That natural coarse aggregate was used in everything. So to make the RCA, or the parent concrete that was then made into RCA, it was the same coarse aggregate stock. So what we're trying to do is keep as many variables constant as possible so that we can see the effects on the recycled aggregate concrete. I also want to point out the adhered mortar contents. So they basically, as the strength of the RCA system increases, the adhered mortar contents going up, which makes sense if you think about the ACI mixer design process. So then this is just some of the proportions in the mixture. So as you can see, we have very consistent weights of cement, fine aggregate, and even our admixtures. The only thing we're changing is the RCA by volume. So what you end up with is, as you increase your RCA percentage, your unit weight goes down, because RCA is less dense than a natural aggregate due to the attached mortar phase. So we're trying to keep the volumes as consistent as possible. So as we increase our RCA content, the unit weight of that system is actually going to decrease. So this is an example batch sheet for the for a PC3 mixture. That's a 6K RCA at 20%. So as you can see, we have 100 milliliters of Cement, which is a super plasticizer. And we use the same amount in every mixture so that we could capture the effects on the fresh properties. So again, we're keeping things as consistent as possible so that we can capture the effects on those fresh properties and especially on the mechanical properties. Now I'm just going to go through some of the results. So these are the fresh properties that we determined according to ASTM C143 and ASTM C138. So we have the slump and the unit weight. And again, as I said, if we're looking at the natural system with no RCA added to it, that's just a natural aggregate system. Our unit weights at about around 149. As you can see, none of the other systems have a unit weight that is that high. They all decrease. So they decrease as you increase the RCA content pretty consistently. So for any 20% mixture, it's around 146 and so on. So these are the compressive strength results of basically every mix we did in the study. So what you're looking at is in A, we have the first parent concrete strength group, and then on the top right, B, we have the parent concrete 2, and then on the bottom, we have the third parent concrete. So again, remember that the parent concretes are increasing in strength as you go from 1 to 3. So what we're seeing here is that the first group definitely did not perform as well. And for the second group, one of the interesting findings was that there actually wasn't a very noticeable effect at all on increasing RCA percentages on the strength of the system, which is actually in contrast to what you would expect. Usually you'd expect that no matter what, if you go from 20 to 100% replacement, that your strength would be significantly reduced. And then for the PC3, we're seeing not necessarily an increase or a decrease, but a little more variability. And what we're really interested in is this strength gain that we're seeing from 28 to 90 days in all of the systems that you're not seeing in a natural aggregate system, right? So there's definitely something going on between days 28 and 90 in all of these systems. This is the splitting tensile strength results. So if you just look at the very left, that's just the control group. So what was interesting here is that the weaker parent concrete RCA groups actually had a higher splitting tensile strength, even at increasing percentages than the rest of the groups. We weren't really focusing on this parameter, but it is interesting to note that the weaker parent concrete resulted in a recycled aggregate concrete system that actually had a higher splitting tensile strength. So then the adhered mortar volume was something that we wanted to capture. So a lot of studies talk about the adhered mortar content, and really all that is a percentage of the recycled aggregate system that is adhered mortar, which we found using the thermal method, as I showed before. So in this study, what we wanted to do is capture the adhered mortar volume. Basically, that's a volume percentage of the entire recycled aggregate concrete system that is made up of that old mortar phase, right? So we can easily use a composite density analysis to look at, a composite density equation to look at the density of mortar in the original parent concrete. And we only know this because we have the mix, we performed the mix, or a previous graduate student performed the mix, and we have all of these values. This is slightly an idealization, but if you think about it, if you basically sum the mass of the sand, cement, and water and divide by the volumes, that's going to give you a pretty good estimate of your mortar phase, because you're basically all you're doing is you're leaving out the coarse aggregate phase. So then we can find the mass of mortar in a recycled aggregate concrete system by taking finding the percent mass of that system that would be composed of the old mortar. And we do that by multiplying the adhered mortar content by the actual mass of RCA that was added to the system, and then expressing that as a percentage of the total system. So then if we multiply by the mass of, however basically a unit mass. So if we're looking at a cubic yard design mixture, then you would multiply by that by whatever the mass of the total system is, and that gives you the mass of mortar in your recycled aggregate concrete system. These two properties can be used together to find the volume of mortar in that system. And if you're using like a cubic yard design, if you're designing, per cubic yard, pounds per cubic yard, you can easily find what the percentage volume of mortar in that system is. So I actually found this to be a pretty interesting result, and it definitely confirms a lot of previous findings on the effect of adhered mortar content. But what we're looking at here, which is a little different, is the actual mortar amount in a volume percentage. So as we increase our mortar volume percentage, our slump is decreasing, which makes sense if you think about that adhered mortar phase. It's a very rough phase, and it contributes to lower workability. Even if it's been brought to an SSD condition, it still has a pretty big effect on the workability of the system. So I found this result to be pretty interesting, and it definitely confirms some other findings in relation to decreased workability with increasing recycled concrete aggregate replacement in an RIC system.
3 minutes left.
Okay, just some findings. So the PC1 group exhibited poorer performance than the PC2 or PC3. There exists an increase in strength of an RIC system that is not seen in a natural aggregate concrete system. And then, and this is really important, in contrast to some other studies, there seems to be some effect on the parent concrete strength on the actual recycled aggregate concrete system. Most people look at it in terms of adhered mortar, but there seems to be some effect of the parent concrete strength. Splitting tensile strength decreases with increasing RCA replacement, and then the PC1 had higher splitting tensile strengths. So then the last thing, which I had just shown you, was that increasing the adhered mortar volume percentage correlated with a decrease in slump. Some of our research questions that we still want to answer is there some level of internal curing? And then, is internal curing the result of adhered mortar? And then finally, what are the hydrates at the ITZ developed around the adhered mortar phase, and how do they actually affect the strength?